Hi, this talk will present a new software program called Arkenza that is designed to help people who stutter to speak fluently over a wider range of conversational environments. Arkenza is being developed by a small software team in the US, and a first release is expected in October 2025. At a high level, Arkenza is an AI-based program to maintain fluency in people who experience developmental stuttering. Why I use the phrase maintain fluency as opposed to regain fluency will be made clear shortly. At present, the Arkenza program is targeted only at adults, or more specifically to people who can read reasonably well. The reason for the reading requirement is that the early graduated speaking exercises in Arkenza involve a lot of reciting text passages that Arkenza generates. Note that Arkenza is a purely software-based program that uses off-the-shelf AI and other inexpensive technologies. Users need only have access to a personal computer and the internet. Arkenza is designed to incrementally expand the range of conversational scenarios in which adults who stutter experience fluent speech through a series of carefully constructed speaking engagements. The Arkenza program starts by having users recite so-called sanitized text passages in unison with a choral reader when they are alone and not within earshot of anybody. By sanitized, I mean that the texts which the users recite are written to exclude all words that the users indicate are fluency problematic for them. Research has shown that people who stutter are remarkably fluent when they recite in unison with a choral reader, or when they recite text when alone. Over a period of several days, users are then exposed to successively more realistic speaking environments in approximately 30 graduated speaking exercises, or GSEs. A foundational principle of Arkenza is that users will anticipate fluency in the current graduated speaking exercise because they experienced fluency in the previous GSEs. This principle is an offshoot of the anticipatory struggle hypothesis, which says that the proximate cause of stuttering is an anticipation of stuttering. The Arkenza Fluency program differs from other programs that attempt to treat stuttering, in that Arkenza does not teach any techniques to improve fluency, such as breathing techniques, fluency shaping techniques, or relaxation techniques. Arkenza's users are encouraged to use any fluency-enhancing techniques that have helped them in the past, or none at all, but Arkenza will not teach any new ones. Arkenza is a purely software-based program, with the only required hardware being a standard personal computer, a webcam, and a headset. Although some homegrown software has been written to implement the Arkenza program, most of the high-tech software that Arkenza invokes is off-the-shelf artificial intelligence and other inexpensive technologies. Arkenza envisions that users will communicate only with their computers or, later on in the program, with remote conversation partners using standard video conference services. Arkenza does invoke some software packages that require significant computing resources, but those apps operate in the cloud, so Arkenza can function effectively on just a standard personal computer. Finally, Arkenza differs from other fluency programs in that its users are expected to be fully fluent in the very first speaking exercise and to remain fluent thereafter. This reduces the anxiety and unease that users might otherwise experience in the program. The Arkenza program can be thought of as a three-legged stool. First, we create a conversational environment in which many people who normally stutter will enjoy fluent speech. In this first speaking exercise, users are alone and are not within earshot of anybody else when they recite prepared text passages. The stuttering literature shows that people who stutter are remarkably fluent when they are sure that their speech is not being heard by other people. Also, people who stutter generally have a keen sense of which words they might stutter on, and they often scan ahead their intended speech to identify problem words and to find acceptable substitute words. So to further improve the likelihood of fluent speech, we use AI to generate sanitized text passages, that is, texts that exclude the use of any words that users have identified as being fluency problematic for them. Finally, it has been also demonstrated that people who stutter are much more fluent when they read in unison with choral readers. So at the starting point of the Arkenza program, the generated text is processed by a text-to-speech app that creates synthetic speech in a cloned voice. And the synthetic speech is piped into the user's headsets. The users recite the sanitized text in unison with their choral readers. So Arkenza uses these emerging technologies to create a starting point for the program. That is, an environment in which many people who stutter will experience fluent speech. The next leg of the Arkenza fluency program is the anticipatory struggle hypothesis. The anticipatory struggle hypothesis postulates that the proximate cause of stuttering is just the anticipation of it. The Arkenza program is predicated on a robust version or corollary of the anticipatory struggle hypothesis. Namely, we postulate that if we can replace an anticipation of stuttering with an anticipation of fluent speech, then people who previously stuttered may experience fluent speech during in-person conversations. The anticipatory struggle hypothesis goes back many years, and a general correlation between the anticipation of stuttering and the realization of it has been shown in multiple research studies. The anticipatory struggle hypothesis has also been shown to be consistent with many peculiar features of the stuttering condition, such as the consistency effect and the adjacency effect. But we would be remiss not to point out that, over the course of the past 10 years or so, the discovery of particular genes that correlate with a propensity to stuttering in individuals and the observation of differences in brain activity in people who stutter relative to fluent speakers has called into question whether the anticipation of stuttering is really the proximate cause of stuttering or just a correlation that is a manifestation of deeper changes in brain structure. So our assumption of the robust validity of the anticipatory struggle hypothesis is just that, an assumption. Clinical testing of Arkenza should determine whether this assumption is correct. The third leg of the Arkenza program is the existing technologies that allow us to create many different speaking or conversational environments, which have varying degrees of fluency stress and conversational realism. Arkenza simply stitches these technologies together to create a set of conversational scenarios that are finely graduated in terms of their conversational realism. This slide summarizes the 4 basic tenets of the Arkenza fluency program. These tenets must prove to be largely correct for the program to successfully change users' expectations of fluent speech in the presence of other people. First, as discussed earlier, people who stutter are surprisingly and remarkably fluent when alone. This becomes the starting point for the program. Second, if stutterers experience fluency in a given conversational environment, they will come to anticipate fluency in that environment. Third, and very important, if stutterers both anticipate and experience fluency in a given conversational environment, they will anticipate fluency in a similar conversational environment. This is important because it allows the Arkenza program to incrementally change the speaking environment for its users, from low fluency stress environments such as speaking while alone, to more realistic environments such as talking to people over Zoom. Fourth and most important, stutterers' anticipation of fluent speech in a given conversational environment will lead to a realization of fluent speech in that environment. As discussed earlier, this tenet is related to, but not equivalent to, the anticipatory struggle hypothesis. Like Newton, who claimed to see a little further because he stood on the shoulders of giants, the Arkenza program benefits enormously from recent, and in some cases, not so recent, advances in several technologies. All of these technologies have been developed to solve other needs and problems. Arkenza is just a happy bystander which benefits from their existence. The top technologies that Arkenza uses are artificial intelligence, including chatbot conversational engines, speech-to-text apps, text-to-speech apps, virtual reality, avatar generation, and video conferencing. Not only do these technologies exist, but they are inexpensive and relatively easy to integrate into the Arkenza software framework. The first technology that we will use is artificial intelligence to generate short text passages for users to recite. The text passages appear on the user's monitors. The AI engine can be instructed to generate text that avoid using any words in a list of words that we supply to it. If this words to avoid list is taken to be a list of words that a user has flagged as being fluency problematic, then the generated text passage is sanitized. That is, it will not contain any of the words that he or she typically stutters on, and so it should be easier to recite fluently. Arkenza also uses artificial intelligence in the form of conversational chatbots, which converse with users. This allows users to carry on conversations, but without the fluency anxiety that would be engendered if their conversational partners were real people. The Arkenza system also makes frequent use of speech-to-text software to transcribe user speech into text. All of the graduated speaking exercises in the middle part of the Arkenza program, for example, transcribe user speech into text. Only that text transcription, and not the original user speech, is transmitted to users' conversation partners during video conference calls. This allows users to carry on meaningful conversations with other people without their voice actually being heard. Effectively, in such GSEs, users remain in a private speaking environment, which is known to promote fluency among people who might otherwise stutter. Arkenza also uses text-to-speech apps in two different ways. First, once the AI system has generated a text passage for a user to recite, we can then pass it to a text-to-speech engine that will create synthetic speech of the text in a cloned voice, which we can pipe into a user's headset. The user can then recite the text that appears on the monitor in unison with the synthetic cloned speech. People who normally stutter are generally fluent when reciting in unison with such a choral reader. So this provides us with another way to improve the fluency of users in the graduated speaking exercises. Our second use of text-to-speech technology is that during video conference calls in which user speech is transcribed into text, that transcription can be synthesized back into speech in a cloned voice. Only the synthetic speech, but not the user's original speech, can be transmitted to the user's remote conversation partner. So once again, the user remains in a private speech conversational environment, which promotes fluency. But in addition, with a little extra AI processing of the speech-to-text transcription, the transcription can be made to be fluent. That is, it will contain zero or only a few disfluencies, even if the original speech was highly stuttered. The system of speech-to-text, followed by processing to remove disfluencies, followed by text-to-speech, comprises what we call the Fluent Digital Twin app. It creates cloned speech with the same meaning as the original speech, but without the stuttering. Some of the graduated speaking exercises have the user recite to or converse with a virtual audience that is created by a virtual reality app. The virtual audience is typically displayed on a VR headset to give a three-dimensional look to the audience. The VR audience can be passive, that is, silent, or active, meaning that occasionally an audience member makes an AI-generated audible response based on what the user says. Conversing with a VR-generated audience provides users with an opportunity to communicate audibly with audiences with varying size, age, sex, and social position, but without the fluency stress normally associated with in-person conversations. In some of the graduated speaking exercises, the user is represented visually in a video conference call, not by a video signal that is captured by the usual webcam, but by an avatar. That is, a computer-generated animated face whose lip and facial movements are consistent with the audio signal. This provides a visual presence for the user in a video conference call, but without the user's stress and anxiety that might be engendered. By knowing that a remote conversation partner could see the user's actual facial expressions. Grimaces, tics, and other facial behaviors often accompany verbal stuttering, so it is not surprising that some people who stutter might feel more comfortable knowing that their true webcam video is not shared through the video conference call. Finally, most of the graduated speaking exercises in the Arkenza program use video conference services like Zoom, Google Meet, or Microsoft Teams to allow a user to communicate with one or more remote conversation partners. The reason for this is that it provides Arkenza with an easy way to control which of several audio and video signals are transmitted from the user to the remote conversation partners. For example, the user's outgoing signals could be the text of user's transcribed speech, synthetic reconstructed audio from the transcribed text, short audio snippets, or full audio, and with regard to video signals, Arkenza can transmit either no video, synthetic avatar video, or full webcam video. Similarly, Arkenza can control which signals from the remote conversation partner are communicated to the user. The combination of these capabilities allows Arkenza to fine-tune the conversational environment, ensuring that successive graduated speaking exercises provide small increments in conversational reality and fluency stress. The Arkenza program is built from individual units that each include a graduated speaking exercise itself and some mechanism to evaluate the user's fluency. In this slide, we assume that the user has progressed to the nth graduated speaking exercise shown in green. The user recites text or converses for an extended period of time in each GSE, and then at the conclusion of each GSE, the user's fluency is measured in some way. This process is repeated for each of the roughly 30 GSEs in the Arkenza program. The user's fluency is monitored by a Fluency Monitor app, which can measure the user's fluency in several ways. The simplest approach, and in fact the approach that will be used in the first GSE, is to simply ask the users for self-reports of their fluency during their speech in the GSE. This approach has the advantage that it should not engender much fluency stress in the user, unlike the other approaches. But this approach has the disadvantage of being pretty subjective. Different users may have widely different internal definitions about what constitutes fluent speech. The other three approaches for a fluency monitor involve some additional user speech or software processing of user speech. The second approach is a simple challenge test. Users recite a prepared text and click on the stuttered words. The system can then compute a fluency metric, for example, the percentage of stuttered syllables. The third approach is also very simple. Arkenza passes an audio sample of a user's speech to an AI engine and asks the engine to rate the user's fluency on a 1 to 100 scale. This approach is surprisingly easy to code, and the AI processing is inexpensive. But extensive benchmarking of this approach against a corpus of audio files of stutterers' speech, whose stuttering severity has been rated by speech-language pathologists, will be required to develop confidence in this approach. The fourth approach could be an implementation of more sophisticated algorithms that are available in the literature. The field of automatic disfluency detection from audio samples is very active, and a number of algorithms have been developed that have reported impressive accuracy. Ultimately, one of these sophisticated algorithms is likely to prove most suitable for use in Arkenza, but it will require significant code development to implement in software. Regardless of how the Fluency Monitor obtains the value of the user's fluency metric, it is passed to another software module, the Promotion Manager. The Promotion Manager then recommends a course of action based on the reported fluency metric and the time spent in the GSE thus far. The Promotion Manager may recommend that the user promote himself or herself to the next GSE, or to remain in the current GSE, or to revert back to a previous GSE. Overall, the assumption is that a user will not proceed to the next GSE until he or she has experienced fluent speech in the current GSE. This slide shows a schematic of most of the hardware and software components in the Arkenza program. My apologies for the size of some of the components in this slide. Yes, there are a lot of components, but as we will discuss later, only a subset of them would be in operation for a given graduated speaking exercise. In the upper left are standard computer hardware components that would be available on most personal computers: a monitor, a speaker, a video camera, a microphone, and optionally a virtual reality headset. The beige box at the lower right illustrates the heart of the Arkenza program, which runs on a standard personal computer. It comprises a set of specialized software modules, or apps, shown in blue. In many cases, these apps are simply software wrappers that facilitate communication between Arkenza and some underlying module that implements a specific off-the-shelf technology, such as speech-to-text, choral reading, conversations with a chatbot, or virtual reality. These underlying modules encompass all the fancy technologies that we discussed earlier. They may reside on the user's computer, or alternately, they may be a service that we invoke from the cloud. The software module files in the Arkenza management system, shown in the pink box, specify which of the many blue or green technology apps are actually turned on for a given graduated speaking exercise. For an individual graduated speaking exercise, the system configuration actually used is a lot simpler than the entire configuration shown here. We will show some specific examples in the next couple of slides. For the first few graduated speaking exercises, the user communicates with no other people, so the communication is basically limited to the apps shown in blue and the user's computer hardware components. But later in the Arkenza program, users communicate with remote conversation partners through a video conference app, shown in green, such as Zoom, Google Meet, or Microsoft Teams. This slide illustrates the system configuration for the very first graduated speaking exercise, in which a user simply recites sanitized text in unison with a synthetic choral reader who recites the same text. The sanitized text driver app receives a list of problem words and a list of topics that interest the user. The sanitized text driver dutifully generates a text passage on a topic of interest to the user and displays that text on the computer monitor for the user to view. The sanitized text passage is also sent to the choral reader module, which generates a synthetic speech rendition of the text in a clone voice, which synthetic speech is piped into the user's headset. In this GSE, the user is expected to recite the sanitized text that appears on the monitor in unison with the choral reading of the same text. After some period of time reciting the generated text passages, the user may indicate to the Fluency management app that he or she wants to be considered for promotion to the next GSE. This invokes the Fluency Monitor app and the Promotion Manager app, as discussed earlier. This slide describes another graduated speaking exercise, one in which a user is represented in a video conference call by a so-called fluent digital twin. The user's speech is first transcribed into text by a speech-to-text app, and with a little extra AI processing of the transcription, a fluent transcription is produced. The fluent transcription is then reconverted back into speech in a cloned voice by a text-to-speech app. The synthetic speech is sent to the audio in port of the video conference client app and also to an avatar generator, which generates an animated face whose lip movements and facial expressions match the synthetic speech. This avatar video stream is piped to the video import of the video conference app. In this way, users can fully participate in video conference calls, sharing both audio and video signals with their remote conversation partners, but neither their original speech nor their original video is transmitted. In effect, users of the Fluent Digital Twin remain in a speaking while alone conversational environment, which is known to be an environment that promotes fluency in people who stutter. The 30-odd graduated speaking exercises that comprise the Arkenza Fluency program may be grouped into 3 campaigns. All of the GSEs in a given campaign share some common features. In Campaign A, No information at all is transmitted from a user's computer to another person. In particular, the user's speech is not recorded, nor is it transmitted to another person. Neither will any text that is transcribed from user speech be transmitted to another person. In this first campaign, users may have conversations with an artificial intelligence conversation engine, such as ChatGPT. And in this campaign, users may recite text to virtual audiences, but once again, only the virtual reality software listens to the user's speech. In some of these presentations to a virtual audience, the audience members may be passive, that is, silent. In other presentations to a virtual audience, the audience members may be active, that is, they may make occasional AI-generated comments based on what the user says. In the graduated speaking exercises in Campaign B, the user's speech is transcribed into text by a speech-to-text app, and this transcription is transmitted to a remote conversation partner over a video conference call such as Zoom. Importantly, the user's speech itself is not transmitted, so the user remains in a private speaking environment. Nevertheless, the graduated speaking exercises in this campaign do represent a step up in conversational realism because users will be communicating, albeit only through text, with another person. Only in Campaign C are the user's spoken words heard, in some fashion, by remote conversation partners in video conference calls. We recognize that going from the graduated speaking exercises in Campaign B, where only a text transcription of user speech is transmitted to the remote conversation partners, to the graduated speaking exercises in Campaign C, in which users' audible speech is transmitted, is a big step up in terms of conversational realism, but also in terms of the level of fluency anxiety that may be engendered in users. So we do what we can to break this big step into multiple smaller ones. For example, in the first graduated speaking exercise in Campaign C, the user recites sanitized text in unison with a choral reader. Only near the end of Campaign C will its graduated speaking exercises transmit the full audio and video of the user to remote conversation partners in video conference calls. Note that these latter graduated speaking exercises in Campaign C differ only a little from standard video conference calls, and in fact they differ only a little from standard in-person conversations. So if users both anticipate and realize fluent speech in the latter graduated speaking exercises of Campaign C, they may come to anticipate fluency during in-person conversations. This slide summarizes the overall status of the Arkenza Fluency program development. The software development is well along, and a first release is expected in October 2025. This reflects the hard work by the Arkenza software development team and the fact that most of the necessary software modules are available commercially. In addition, there has been some testing of individual software apps, including the problematic word identifier, the sanitized text generator, the choral reading app, a web-based OASIS form, a user fluency self-rating module, a promotion module, a speech-to-text app, the text-to-speech app, and the ChatGPT conversation module have all been exercised. But significantly, there have been no end-to-end clinical trials of the Arkenza Fluency program itself to assess its effectiveness. That's not because we don't recognize that Arkenza needs clinical testing before it can be released for general use. Far from it, we have identified quite a number of issues that need to be addressed through clinical testing, which are described in an appendix to this talk. But a proper clinical trial for Arkenza would require careful IRB review and supervision by experienced speech-language pathologists or university researchers. The Fluency AI team that is developing Arkenza currently includes just a retired physicist, a handful of software engineers, and a grandmother, none of whom is a speech-language pathologist. We are actively seeking partners to carry out the necessary clinical trials so that the promise of Arkenza can be properly assessed. We point out that a clinical trial of Arkenza even if it proves that the program does not ultimately change stutterers' anticipation of fluency when conversing in person, may still yield useful information about the stuttering condition. In particular, it may shed light on the robustness of the anticipatory struggle hypothesis. In addition, some of the software modules that have been developed for Arkenza, such as the synthetic choral reader and the sanitized text generator, may find application in other studies of stuttering behavior. In summary, this talk has described a novel software-based fluency program, Arkenza, that is under development at Fluency AI LLC. It starts users in a conversational environment in which many people who stutter enjoy fluency. That is, private speech recitations in unison with a choral reader. Arkenza then leads users through a series of graduated speaking exercises that incrementally add ever more realism to the conversational environment. Based on the anticipatory struggle hypothesis, we expect users will anticipate fluency in a current graduated speaking exercise because they realize fluency in previous graduated speaking exercises. The software development process has been pretty fast because most of the sophisticated software components, including AI, are available off the shelf. But we recognize that extensive clinical testing will be required to determine whether Arkenza does in fact change users' anticipation and realization of fluency during in-person conversations. We are looking for partners to conduct the clinical trials. This concludes our presentation of the Arkenza Fluency Program. There are 3 appendices to this talk that follow. Please feel free to send comments and questions to me at the email address given here, steve@fluencyai.net. I thank you for your attention. This appendix lists some of the outstanding issues that would need to be resolved with clinical testing of Arkenza. The first and foremost question is, does Arkenza actually work? That is, at the end of the Arkenza program, are any of its users fluent when talking in person? If the answer to this question is no, then most of the other issues are obviously moot. But proving a definitive no is not so easy, because Arkenza's framework can be configured in many ways, and some may work while others fail. So addressing the other issues may help us to identify how to tune Arkenza's framework to improve the fluency outcomes of its users. The second question is, if some of Arkenza's users retain fluency at the end of the program, but not others, is there a correlation between the success rate and the level of disfluency at the start of the program? That is it possible that Arkenza might be effective at improving the fluency of people with a mild stutter, but not a severe stutter? Similarly, if some of Arkenza's users retain fluency at the end of the program, but not others, is there a correlation between the success rate and the length of time the users spend in the GSEs? Obviously, if spending more time on the GSEs improves the fluency success rate, then we could improve the efficacy of the program by suggesting or mandating longer graduated speaking exercises. But there is also an obvious trade-off. If the required time is too long, users will drop out or won't start in the first place. If they are told, for example, that the program will require 2 weeks of their time. Finally, if some of Arkenza's users retain fluency at the end of the program, but not others, is there a correlation between the success rate and the fluency metrics that the users achieve during the program? Addressing this issue will help us identify the appropriate values of fluency metrics that are used by the promotion manager to decide when to promote users to the next GSE. But in addition, it may allow Arkenza to identify users who are unlikely to benefit from the program and to do that early in the program rather than later in the program when they have invested more time. A standard issue to be addressed through clinical testing is attrition. How many users drop out before completing the program? And if they do, why? How far do they proceed through the program before dropping out? And is there some critical GSE that seems to be a problem? We believe that requiring Arkenza users to refrain from normal in-person conversations for the duration of the program is likely to be necessary to retain fluency throughout the program and beyond. But we also fear that this requirement is going to be difficult. Difficult in two ways. First, it may be psychologically challenging to users, and second, it may lead to excessive attrition, or it may cause many potential Arkenza users to not start the program in the first place. Clinical testing is needed to address these issues. The flip side of the previous question is, just how important is it that users of the Arkenza program refrain from normal conversations during the course of its graduated speaking exercises? Possibly, it may be important for users to refrain from normal conversations early in the program, but perhaps this hermit-like rule could be relaxed later in the program. We recognize that this is a critical issue. The Arkenza program may not be attractive to many potential users, even if it is proven effective, if the program requires a week or two without normal in-person conversations. The next issue is, which of the graduated speaking exercises actually expand the range of conversational environments in which people who stutter speak fluently? This issue is of obvious relevance to the design of the Arkenza software program and its duration, but it is less clear how to address this issue through a clinical testing program. Possibly, we would have to rely on surveys of user opinions about which GSEs seem to provide the maximum benefit. Next, we are reasonably confident, based on our reading of stuttering research, that the 3 Arkenza campaigns are properly ordered in terms of increasing conversational realism and increasing fluency stress. But we are less confident about our currently defined ordering of GSEs within individual campaigns. This issue might be addressed through user surveys, or alternately by giving users some discretion about which GSE to perform next and recording their selections. It's also possible that the same GSE ordering might not be optimal for all users, which would be a tougher question to address. The next 2 issues have to do with the Fluency Monitor and the Promotion Manager. From a coding perspective, the easiest way to obtain a fluency metric from a user's speech during a GSE is to just ask them for a self-rating, such as very fluent, fluent, reasonably fluent, or not so fluent. This approach also has the advantage that it imposes no additional fluency stress on the users, since no additional speech is required, nor does any additional software listen to their speech. But it has the distinct disadvantage of being rather subjective, in that users may have widely different notions about what constitutes fluent speech. But we don't necessarily care about whether users' definitions of fluency are consistent with one another. Instead, we care much more about the final outcome. For example, if users who consistently self-rate their fluency as being fluent or very fluent drop out of the program at widely different rates, then we might conclude that fluency self-rating is not a good way to inform a decision about promotion to the next GSE. By contrast, if users who self-rate their fluency throughout the GSEs as being fluent or very fluent do consistently complete the program, then we might conclude that fluency self-rating is a sufficiently good way to inform the promotion decision. The alternative to fluency self-rating is to compute a fluency metric from user speech. We discussed 4 approaches to do that earlier. The issue, which requires clinical testing, is whether the presence of that software-based listener creates excessive fluency stress for some or all users, thereby immersing the users in a speaking environment that promotes disfluency rather than fluency. A related issue is whether fluency metrics that are computed by some sort of software algorithm are sufficiently accurate to be helpful in deciding when to promote users to the next GSE. On a conceptual level, clinical testing should also reveal which of the 4 tenets of the Arkenza program, if any, are true. Resolution of this issue might be of interest to the speech-language pathology community, even if Arkenza itself proves to be an ineffective program to improve fluency. The next question bears on the important issue of the total duration of the Arkenza program, which in turn will affect its attrition rate. What is the minimum duration of each GSE to change users' expectations of fluency in their speaking environment? Next, the Arkenza program assumes that reciting text that has been sanitized to remove problematic words reduces fluency stress compared to reciting unsanitized text. But this should be confirmed with clinical testing. The next several questions have to do with the qualifications and characteristics of the remote conversation partners with whom users converse during video conference calls. Are there any personal characteristics that make a remote conversation partner a better or a worse participant in an Arkenza program? Would it be sufficient for users to have video conference calls with friends, family, and colleagues? Should there be any training of the remote conversation partners to be understanding of what the Arkenza users experience during the program, their hopes and fears? Related questions are whether Arkenza users could communicate with each other during the GSEs in Campaign C rather than friends and family. Alternately, in Campaigns B, N, or C, is it helpful or necessary for remote conversation partners to be speech-language pathologists? With regard to the generation of user-specific lists of problematic words, it will be important to learn whether the exercises that define the list of fluency problematic words for users could bring harm to them by drawing attention to their problematic words and thereby increasing anticipation of speaking them disfluently. And clinical testing should be able to identify the best method to identify problematic words, such as clicking individual words in a list versus clicking words in text passages. Finally, clinical testing should be able to identify the fraction of people who stutter who cannot get out of the starting gate. That is, who do not experience fluency in the very first graduated speaking exercise when Arkenza does everything possible to make their speech fluent. The final three questions have to do with user fluency in the post-Arkenza period. The first question is, for those users who do experience good fluency at the end of the Arkenza program, does that fluency persist indefinitely or does it diminish over time? If the fluency does diminish, over what time frame does it deteriorate? And if the fluency does diminish, can fluency be recovered by revisiting some of the GSEs? If so, which ones? The questions listed in these preceding slides probably do not represent a fully complete list of all the issues that can and must be addressed through clinical testing of Arkenza. But we hope that they represent a good starting point, and that resolution of these questions could determine the effectiveness of Arkenza in terms of expanding the range of conversations in which people who previously stuttered remain fluent and also inform decisions about how to make it more effective. This really does complete our presentation of the Arkenza Fluency Program. Thanks for hanging in there. Please feel free to send comments and questions to me at the email address given here, steve@fluencyai.net. And thank you for your attention.